Welcome back. It's time for Astronomy in the News for April 2017. That's the year we're in, right? Okay, so first up, the moon Enceladus of Saturn. So Hunter Waite of Southwest Research Institute, the guy down in the right-hand corner there. Southwest Research Institute is located just down 35 in San Antonio. I've got several friends. I think all of us have several friends who work down there. He used the Cassini probe that's currently orbiting Saturn. He used an instrument on it called the mass spectrometer and flew it through a plume of water coming out of a geyser on Enceladus. And what he discovered is that there's a lot of molecular hydrogen in that plume. Now that sounds kind of, whatever, boring, but why this is really important. So molecular hydrogen, one, we generally don't expect it to be around. So, we're standing in the room here where the atmosphere is full of oxygen and nitrogen and water, but very, very, very little molecular hydrogen. Molecular hydrogen is formed, however, on deep sea vents underneath the ocean. This molecular hydrogen is feasted on by primitive bacteria that inhabit the deep sea vents. So this is suggesting that they're the same process that happens deep in Earth's oceans could be happening deep in the oceans of Enceladus. So there's the possibility for life. We've kind of know that water is a great place for life. This is a pretty exciting opportunity. There is one downside to this, however. The fact that he discovered so much molecular hydrogen within these plumes means that there's probably not a whole lot of bacteria eating it up. So the plus side is there's geology happening on Enceladus that's very similar to that on Earth. There's a good possibility that the conditions for life are right underneath the surface of Enceladus, but as yet, no actual direct evidence for life. So give NASA lots and lots and lots of money and they can go send a probe down into the deep oceans. We'll build the first Enceladus submarine. Okay, next up, Planet 9. You might remember this in the news from about a year ago. This is a hypothetical entity that explains the orbits of a bunch of the very distant minor planets in our solar system. So what we're looking at here, here's the sun. Pluto's orbit is probably about where that circle is. All of these other things out here are much more distant objects that are about the size of Pluto, more or less. And you'll notice that they're all kind of on this side of the sun. And there's none of them over here. So Planet 9 is proposed to have an orbit something like this. And it's on this side and is big enough and massive enough that it causes everything else to sit over on this side. So this was purely hypothetical. However, there's been a search by Australia National University going through a large sky survey looking for small little things that are moving in the night sky. And with the help of 60,000 normal people like yourselves going through millions of images, they've identified 4 possible candidates for Planet 9. So this study was led by Brad Tucker of Australia National University. If you've been coming here a while, you might remember Dr. Destructo. He came and gave a talk. I believe it was about supernova, my favorite topic. So he led this survey and is going to be following it up with his team at Siding Springs Observatory in Australia. Hopefully we'll have direct pictures and direct evidence of Planet 9 within about a year or so. All right, next up, Aya Higuchi used ALMA, which is a radio telescope down in Chile, and she looked at debris disks around young stars. Debris disks are the things that cause lots of the small little dust grains and stuff that are left over in our solar system. It's left over from planet formation. And comets, yes. So she's particularly interested in the smallest grains that are in these disks and why they survive as long as they do. So one of the questions is is this material primordial? Does it come from before the solar system forms, or is it something that occurs after the solar system's already formed and somehow processes within the disk in the solar system kind of allow it this dust to persist? One of the problems is the sunlight should push a lot of these dust grains away, and so they shouldn't really stick around. So she looked for signatures of carbon gas within these disks. Carbon gas, we have carbon dioxide in the atmosphere. This is carbon, atomic carbon that's in gas form itself. She found evidence of a lot of carbon within these disks, as much carbon as there is in the disk in carbon monoxide gas, which hopefully none of you have in your homes. So there's a lot of atomic carbon. This was very unexpected. One of the things that's expected is that anytime there's free carbon sitting around, it's going to get together with hydrogen, and it's going to make methane, and it'll go off and do its own thing. Doesn't really stick around. But the fact that she found a lot of atomic carbon means that there's no molecular hydrogen, which means the molecular hydrogen's all been blown away by the star already, and so all the carbon that's left is being knocked off of the remaining little bits of dust grains, and those gases that persist allow the dust grains to stick around. They kind of help the dust grains shield themselves from the light from their parent star. So this is explaining how some of this, or might explain how the dust grains that exist in debris disks last for millions or billions of years like they are in our solar system. All right, next up, starting observations this month is the Event Horizon Telescope. This is a network of radio telescopes that span the entire globe. So what we see on the images here, a series of radio telescopes. These are just kind of showing the lines, showing how far apart they are. But in Chile, down in Antarctica, Hawaii, throughout the U.S., some in Mexico. Let's see. That's, I think, Italy and Spain. Some of the radio people here might know better than I. But so what they're doing is pairing all of these telescopes together, and they're trying to look at black holes in the centers of the galaxies, supermassive black holes, and looking down so that they can see the detail at the very, very, very edge of the black hole. So this is something we've not been able to do before. Black holes tend to be relatively small. So a black hole the size of the sun is, about the size of downtown Austin, maybe even a little smaller than that. Pretty small, about 3 kilometers in size. Supermassive black holes in the centers of galaxies, however, can be about the size of our solar system. And, our solar system is pretty big, but in galactic terms, that's extremely, extremely small. But by networking all these telescopes together, we can peer down and actually manage to see essentially the edge of the black hole and try to find out what is actually happening, whether physics, as Einstein explained gravity to us, actually still holds at those small radii. So this system of telescopes is taking their first images this month. We'll probably start hearing about what they find, maybe later this summer, or certainly by the end of the year. So stay tuned on this. All right, next up, Chun-Ji Lee, I'm probably butchering his name, used the Hubble Space Telescope to take a look at a supernova remnant in the Large Magellanic Cloud. Dr. Boom was just talking about supernova. This is a remnant that's about 1,000 years old. It is a type 1a supernova, so not one of the ones that Dr. Boom described. This is one of the ones that I actually study that are white dwarfs that explode. One of the big questions in this type of supernova is what type of star system causes the explosion. So you can either take 2 white dwarfs and crash them into each other and they explode, or you can take a single white dwarf with another regular star around it. You dump a little bit of gas from that companion star onto it, and it gets to a certain mass and it blows up. We have no idea which of these scenarios is correct. We're still trying to figure that out. But in his study, in the center of the supernova remnant, so what you're looking at here, this kind of red gas here, is the remnant of the supernova. The supernova itself exploded somewhere down over here, and he peered into that area in the center and identified the star that is very, very, very close to the center of that explosion, about the size of our sun, that might be the companion star to the white dwarf, which tells us that of the two possible mechanisms, this particular system might have had a white dwarf and a regular sun-like star next to it that transferred material over. We've only got 2 instances of systems that might have a star like this. So, and this is number 2. So we're all very excited about the possibility that this might give us strong evidence of exactly how these types of stars explode. All right, and finally, so we have Marco Hiberge from, I didn't get where he's from. He was taking a look at a quasar, excitingly named 3C186. So this is a picture of this particular system. And what we have here, this really bright thing here is the quasar itself. And the fuzzy area around it, you see it's a little bit brighter here than it is over here. This is the galaxy that the quasar lies in. So a quasar is a supermassive black hole that's gobbling up a whole lot of material. We've seen plenty of quasars, but we always find them in the center of the galaxy. This quasar, the galaxy, you see the oval here, the center of the galaxy is right about there. That quasar is pretty well offset from the center. Now, this is both completely expected and completely unexpected. As I said, every other quasar we've seen has been in the center of its galaxy. However, the fact that it's associated with supermassive black holes are something like 10 billion times the size of our sun. We don't think they form that big. We think they form about, maybe 10 times the size of our sun, and a whole bunch of them merge together and eventually, over billions of years form these really, really large black holes. However, one of the problems with this scenario is when 2 black holes merge, there's a very good chance that there's the way that they merge together, it's not perfectly spherical. They kick off a lot of energy in one particular direction, and so those black holes get kicked out of their galaxy some great distance. However, we've never actually seen this occur. So this is evidence that the supermassive black hole probably underwent a merger with another really large black hole sometime in the past, probably a couple 100 million years. And it kicked this entire thing out of the center of its galaxy, out into the kind of the edges. It's been picking up gas and dust on the way and eating it, and that's why we see the quasar itself. So this is both a confirmation that our ideas of how black holes merge are probably right, and exciting the fact that we've actually finally seen it happen, which is somewhat unexpected. All right, that's all I have for news for this month. Thank you. Oh, we have a point. We have a point of order.
There will be an asteroid coming within 4.5 lunar distances from here.
Ah, so I've just been informed. There will be an asteroid coming within 4.5 lunar distances. So astronomically speaking, a very, very, very near miss, but far enough away that we don't have to worry about it. I'm assuming. Is it going to be, I assume it's not going to be visible with the naked eye. No. So not visible with the naked eye. You can probably keep an eye. Is NASA going to have a webcast or something? So keep an eye on the NASA website. You'll probably be able to watch it yourself, watch video of it yourself on NASA. All right. That's all I have. Thank you very much.
Thank you, AstroBit.